Hey everyone, I wanted to get on and make a video giving you some tips about chirality and chiral centers, assigning RNS in particular, because I noticed a lot of people were having questions about this, and generally we're struggling a little bit about kind of flipping molecules in their head. And again, I'm going to say I know this is one of the harder things conceptually to learn, because you have to teach yourself to rotate 2D objects three-dimensionally in your head. And again, I know this is complex, and really we just have to practice a lot to kind of get used to it. But I'm going to show you some tips and tricks to help some of these problems be a little simpler for you without trying to always redraw the molecules and rearrange. So first of all, I'm going to talk about a reminder of chiral centers. So remember, a chiral center is any carbon you see that has 4 different groups bonded to it. So for example, in this molecule I have shown here, this is a chiral center, and that's because bromine is one group, hydrogen is another group, and then this whole carbon chain is a third group, and this whole carbon chain is a fourth group. And notice there are 4 different things, and so this is a chiral compound. Now let's talk again about assigning. One of the main ways to assign, when you see a compound drawn this way, where you have the wedges and the dashes, is you always put the group of least priority in the back. So it needs to have a dash in the back, and that's the group of least priority. Usually this will be a hydrogen. It is not always a hydrogen. Sometimes your group of least priority can be something with a carbon on it, but it is, again, lowest priority. But in the examples we're looking at today, I'm going to be using hydrogen as my lowest priority group. Generally, we ignore this. It goes in the back, and then we don't think about it, and we're going to assign priorities to everything else and figure out our RRS configuration. So for this compound, to assign your priorities, remember you want to first look at the atomic number, which is also the atomic weight, atomic number of the attached groups to the chiral carbon. So one by one, I'm going to look at what this chiral carbon is attached to. So it is attached to a bromine, a hydrogen, and it's directly attached to a carbon here. Now I'm talking about direct attachment. It has a bond to a carbon, and it is also directly attached to a carbon here. So first of all, I can tell you that bromine will get our highest priority. And as I said, hydrogen will get our lowest priority. Now this is just based on the atomic number, right? If you look at a periodic table, hydrogen, of course, is number 1. It's going to always get lowest priority if it's there. It gets a 4, and bromine will get a 1. But how do we distinguish between these 2 carbons? Well, we're going to then look at what these carbons are attached to and decide from there the priority. So these carbons that I have drawn, what are they attached to? Well, the carbon on the right, here it is. Don't forget it has 2 hydrogens here. They're not drawn. So it has a hydrogen, and it's attached directly to a carbon here. This carbon on the left has a hydrogen, and it's directly attached to a carbon. Well, those so far are still identical. So we're going to go one further and see if we see any differences in what the next carbons are attached to. Okay, so now I'm talking about these 2 carbons and what they are attached to. This carbon here on the right is attached to, they're not shown, but 3 hydrogens. Okay? And this carbon on the left is attached to 2 hydrogens, and it's directly attached to 1 carbon. So now we have a difference. And the one that is different, that has a higher atomic number compound, is the one on the left. So the one on the left is going to get, the group on the left will get higher priority than the group on the right, even though they are carbons on each side. So that means this group will get 2 and this group will get 3. Now again, I'm ignoring my hydrogen in the back. I'm going to connect the 1, 2, and 3 and look at if this is clockwise or counterclockwise. So in this case, it is counterclockwise, which means that this is an S rotation. Okay, now, what if I give you a compound like the one drawn here, where the hydrogen is wedged forward instead of any other group being wedged forward? Now, you could redraw this and try to rearrange it so that the hydrogen is the thing that is wedged, or excuse me, dashed in the back. But I'll give you a tip on how to deal with this situation on any compound when your hydrogen is wedged forward. So again, let me be clear. This is a situation for when the lowest priority group is wedged forward. And I'm being very clear, it has to be wedged. It can't be one of these regular lines like this. It has to be the wedged line. So your lowest priority group is wedged forward. If you are in this situation, which this situation will crop up quite a lot, you've already seen it on many problems. You can try to rearrange the molecule, turn it around, look at what it looks like when the hydrogen is in the back. Or what you can do is assign the molecule as normal, and then whatever you get based on your assignment, it will be the opposite. Okay, so here I'm going to ignore the hydrogen again. So I'm doing it as normal as if the hydrogen was in the back. I have the same groups as I do on this compound. So my assignments will be the same. Bromine will get 1. This chain here will get 2. And this chain here will get 3. So if I draw my arrow, this is now going clockwise, which you would assign as an R. But because we are doing this situation where the hydrogen is in the front, that means that the real chiral center is actually S. So actually, this molecule is the same as the one I drew on the left. And if you can't see that at first, what I want you to look at is all I've done is actually flip the molecule down so that, for example, this point goes up and this point goes down. So my bromine has gone down on the other side and my hydrogen has gone up. So these are the same, and I can tell that because the other way I can tell that is if I look at the numbering of the structure. This is 1, 2, 3 bromo, and it is an S. And this is also 1, 2, 3 bromo, and it is also an S. So you can tell these are the same compound. Okay, you can also do this in rings as well to figure out if something is the same or not. So I've shown a ring below Again, varying situation where I have a hydrogen wedged forward or I have the bromine wedged forward. Now here, I'm going to start with the ring that is in our normal positioning with the hydrogen in the back. Remember, for rings, the way that we think about which will get higher priority is by going along the ring all the way around and seeing if and where there are differences at each point along the ring. In this ring, the bromine will get highest priority. This carbon here will get second highest priority. And this carbon here, which is attached to the chiral center, will get third highest priority. So if I draw my arrow, that means this is a clockwise, which means it is R. Okay, let's look at our other ring. Our hydrogen is wedged forward here. So we are in the situation I talked about. Bromine will get position 1. Again, our carbon here with the double bond will get 2, and this one will get 3. If I go around, that's clockwise, which gets R, but because our hydrogen is in the front, this is actually an S. So these compounds are actually enantiomers of each other. They are mirror images. And if I were to take one of them, they are non-superimposable mirror images. If I was to take one of them and mirror it here, so for example, if I draw this ring, but mirrored, it would look like this. And this compound is this, except just flipped around. And again, I can tell that they're enantiomers because of their chiral centers. Enantiomers always have exact opposite chiral centers. So this is an S and this is an R. If you had two chiral centers, for example, the enantiomers would be SS and RR, or something like SR and RS. Again, the chiral centers will always mirror each other as well. This is another way to tell if something is an enantiomer. But the main criteria is that they are non-superimposable mirror images. Okay. That is it for tonight. I hope that tip helped you and you can use it instead of having to rotate a molecule to be able to assign some of your R's and S's.